Let's do a recap of today's lecture about slant asymptotes and other kinds of asymptotes and how they relate to polynomial division. So here we've got a rational function, and it's not really obvious how the numerator might factor, which would always be your first step, is to try and figure out whether you can factor anything and then see if any terms cancel. But what we could do here is we could actually perform the polynomial division. And as someone in class mentioned, if we've got a cubic function divided by a linear function, you should expect the result probably to be quadratic, because if you have x cubed divided by x, that would simplify as x squared. But of course, the division might not happen evenly, so you'd have a quadratic with a remainder. So let's actually kind of see how that plays out. We'll do the division, and we'll hope at the end to see a quadratic with a remainder. So x plus 11, and we're dividing by x plus 2. And if you remember the process here, I'm looking for a term here where something times x gives us x cubed. So clearly x squared times x would give us x cubed. And then x squared times 2 gives us 2x. And now you subtract. So the, x cubed minus x cubed is 0. X squared minus 2x squared is negative x squared. And now you do it all over again. So what term here could I multiply by x to give us negative x squared? And the answer is negative x. So when I do that multiplication, I get negative x squared. When I multiply negative x by 2, I have minus 2x. And now I subtract again. This minus this is 0. And then I have the x way up here is sort of matching up with the minus 2x. So x minus 2x gives us 3x. So last step, I know 3 times x will give me the 3x. 3 times 2 gives me 6. So now I can do the subtraction. That gives me 0. And 11 minus 6 is going to give me a remainder of 5. Okay, so I've performed the division, but what does that mean for my original equation? So when I have this cubic divided by the linear expression, I end up with this as the answer. I've got x squared minus x plus 3, and that's what I was expecting to see, because I know that x cubed divided by x should give me some second degree equation, some x squared equation. But it didn't divide evenly, remember, because we've got this remainder of 5. So the way that you would represent that is you would add 5, but it's still being divided by x over 2. So whatever your remainder is, you're still dividing it by whatever you were originally dividing it by. All right, so we've performed the division, but what has this told us about asymptotes? So let's imagine drawing the graph. I am interested in what the graph of this green function looks like, f of x. And we know the green function can be written in terms of two parts. We've got this part, and then we've got the red part here. So let's think about the overall y value as the y value that you get when you plug x into the black part plus the y value that you get when you plug x into the red part. So let's just look at a couple of points and then draw a general lesson. So if I plug 10 in here, 10 times 10 is 100, minus 10 is 90, plus 3 would be 93. So what that tells us is, so that's 93. So the y value of just this quadratic is 93. What about this additional y amount? So 5 divided by 12 is 5/12. So that's a very small number compared to 93. So this would be 5/12. And I know that the black height plus the red height is where my actual y value for the green function is. Because if I plugged in x equals 10 to this function, that would be the same as if I plugged in x equals 10 to that function. Okay, so that's at x equals 10. Let's see what happens much further down when x equals 100. When x equals 100, 100 times 100 is 10,000 minus 100 plus 3. So that's like 9,903. I'm going to draw something that is like really not at all to scale. So 9,903. So clearly as x is getting larger, the quadratic is getting much, much larger. The y value is coming out of the quadratic. What are the y values for this red term doing? So when x was 10, the red term was 5/12, very small. When x is 100, we got 5 over 102. So that's like even smaller. I'm going to represent it with like a single dot here. So 5 divided by 102. Okay, I forgot what my last sentence was because I got interrupted, but at x equals 100, right, so we've got, so the red term has a very small value when x equals 10. It's got a much, much, much smaller value when x is 100. And I hope that you can see that as x gets larger, this term is going to get smaller and smaller and smaller, approaching 0. So if I want to know what's happening with the green function, what's happening is it is getting closer and closer and closer to this quadratic function. Let me draw, I'm going to connect the black values here. So this is the quadratic function, and then the red amount is getting the red amount, which is how far our function is above the quadratic, is getting smaller and smaller and smaller, which I didn't represent very well in this picture. But that is why you could refer to this equation as the asymptote. And I like to call this term over here the error term. And the reason I call it an error term is because this term is never equal to 0, which means that our original function is never exactly equal to the quadratic function here. It's always a little bit larger or a little bit smaller. But the amount by which it's larger or smaller is very, very tiny. And that's especially true as x goes to infinity, because this amount that we are above the asymptote is getting smaller and smaller towards 0. Okay, so it's not usual in pre-calculus classes to refer to a quadratic asymptote like this, but I think it fits the idea of an asymptote well, because the idea of the asymptote is it is a curve that your curve is approaching as x approaches infinity. So in our class, I'm perfectly happy to call this a quadratic asymptote. Usually they'll ask you, like, is it a horizontal asymptote, which would be, just a horizontal line, or is it a slant asymptote, which refers to a linear equation? So if this had come out to be a single number or a linear equation, then that fits the two standard forms of asymptotes you would see. But using this idea of an error term, you could write, literally any equation you want here and have an error term. And as long as your original equation is simplified to look that way, you could think about your original equation as approaching whatever function this was. So let's do one more example where we go backwards. Let's say that I want to write a rational equation that has a slant asymptote of 2x minus 1. So in other words, if I have the graph, I would have an asymptote like this, which is the equation 2x minus 1. So I could start out with the asymptote there. The error term could look like anything as long as the limit of this term as x approaches infinity goes to 0. So the only requirement here is that this gets smaller and smaller and smaller as x gets larger. So if I keep the error term the way it is right now, you can see that if I plugged in x equals -2, that would give me a vertical asymptote at -2. So that would be, let's put that right here. So this is x equals -2. But if I wanted to write this as a rational function, all I would need to do is put this over the same denominator as this. So let's do that off to the side here. I would have 2x minus 1 times x plus 2 over x plus 2, and then add that to 5 over x plus 2. And so then I'd multiply it all out, and what would I get? I'd get 2x squared, and then plus 4x minus 1x is plus 3x. And then I'd have minus 2 plus 5, which is plus 3. And then it's all over x plus 2. So now I've done the problem backwards. I could have started off this way and asked you, what does this rational function look like, you would have performed a polynomial division on it. At the end of your polynomial division, you would have said, aha, this equals 2x minus 1, but there's a remainder, and the remainder is 5. And so that would have given you this, and then you would have said, aha, so now I've got an asymptote at 2x minus 1, and I've got this error term. And so we know that our curve would look something like this. And I'm not drawing it on the other side of the asymptote here. And you'd be done. So I think it's helpful to think about going in both directions. You're starting here, you do the polynomial division to break it apart into the result and an error term. Or you could start with what you want the asymptotes to look like and then combine them back together to get a rational function. What if I wanted to have this asymptote, but I didn't want any vertical asymptotes at all? I mean, you could imagine, like, we could change the error term to put the vertical asymptote wherever we wanted to. So we could make like x minus 5, and now it would be the same slant asymptote, but the vertical asymptote would move over here to plus 5. But what if we want no vertical asymptote at all? In that case, I'd need some kind of denominator here where it's not possible for the denominator to be 0. So that can't happen with a linear term like this. I'd have to have a prime quadratic factor. So for example, if I had 2x plus 1, you remember, if you imagine x squared plus 1, that's like an upshifted parabola. And so because this has no zeros, that's an easy way of seeing that the denominator here can't be 0. And if the denominator here can't be 0, that means there are no discontinuities because all the values are defined. So, but the question is does this still work as an error term? Like, I changed it quite a lot when I made it from a linear term to a quadratic term. But the answer is, yeah, it works perfectly well as an error term because as x gets larger, this is still approaching 0. So let's now combine this together into a rational function. I can do the same thing. I would put this over the same denominator as that one. Let's do this off to the side. So I'd have 2x minus 1 times x squared plus 1 over x squared plus 1, and then the plus 5. And so now I just need to multiply this out. So let's do it. I've got 2x times x squared is 2x cubed. Here I've got 2x times 1 gives me 2x. Here I've got minus x squared. And then here I've got negative 1 times 1 plus 5 is 4. And then this is all over x squared plus 1. So you see it's a totally different rational function than we had before. Now I've got a cubic on top and a square and a quadratic on the bottom. But if you think about a cubed divided by a squared, you're still going to end up with a slant asymptote. It's just that the particular denominator we have means that there are no discontinuities because all x values that we plug in would produce a well-defined output. So in this case, if we wanted to know what the graph would look like, we've still got the same slant asymptote at y equals 2x minus 1. The only difference now is there's no vertical asymptote. So I'm noticing that this term is always positive no matter what. So what that means is we're going to end up having something like, what is it? Hold on, let's think this out for a second. What should the y value be when x is 0? So let's see, that's going to be 0 minus 1 plus 5 divided by 1. So that's going to be 4, so like up here. So it should be something like this. And the reason I know it never crosses this asymptote is because what would have to happen for us to cross the asymptote is the error term would have to be negative. Because remember, the asymptote is this equation. So if I wanted my function to be below that equation, I would have to have that equation minus something. But this term is always positive for all x values, therefore my function is always above that asymptote equation. Okay, well, I hope this set of examples was helpful to think about. Good luck.